Hi, welcome to this FMSP online revision recording. In this recording we're considering Edexcel FP3 and we're putting together the sort of definitions and graphs and basic properties of hyperbolic functions and their differentiation in this particular session. So there's another session about integration where we'll cover that, but in this session we'll just restrict ourselves to the differentiation of hyperbolic functions. So first of all, we need to know the definition of the 6 hyperbolic functions in terms of exponentials and their graphs. So for example, we need to know that cosh of x is defined to be e to the x plus e to the minus x over 2. So that's a definition of cosh in terms of its exponential. And following from that, we can work out what the graph of cosh of x would look like. So a nice way to think about this actually is to imagine that we have the graph of e to the x, which is something like this. So that's y equals e to the x, and a graph of e to the minus x. So of course that will just be the same graph but reflected in the y-axis, replacing x by minus x. And then the graph we want is just the average of these two. It's summing and dividing by 2, so it'll always be exactly halfway in between these two graphs. So the graph of cosh x looks a bit like a kind of quadratic, although it isn't actually a quadratic, with a minimum at 0, 1. We need to know about inverse hyperbolic functions, their graphs, their properties, and their log equivalents. So if we stick with the example of cosh, then the inverse cosh function x, just like we can define cosh in terms of e, we can define inverse cosh in terms of log, and that one is log of x plus the square root of x squared minus 1. So if we need the inverse cosh of something, we need to know what cosh is to a particular value. We can use that log function to do that. We've got differentiation of hyperbolic functions. So for example, if y is cosh x, then dy by dx is sin x. And of course also involving the inverse trigonometric function. So once again, if y is arc cosh of x, then dy by dx, so the derivative of that one will be 1 over the square root of x squared minus 1. So there are lots of other standard formula that you need to know for this, and that should include trigonometric inverse functions as well, so arc cos, arc sine, and so on. Okay, so let's have a look at some questions about these ideas. The first one we've got is working with the definition of sin and cosh in terms of exponentials. So it says, starting from the definitions of sin and cosh in terms of exponentials, prove this statement. Now, I would always recommend that you start with the side in which either sin or cosh or the simplest functions appear. So I would say that sin x is simpler than cosh 2x in terms of working with its exponential definition. So in my solution down here, I'm actually going to start with the left hand side. I'm going to look at 1 plus 2 sin squared of x, and I'm going to substitute for sin x its exponential definition. So we've got 2 times e to the x minus e to the minus x over 2, and we're going to square that. So the bracket there is the definition of sin x in terms of e to the x. So we've got 1 plus, and then we'll have 2 over 4 if we square that 2. Now if we square e to the x minus e to the minus x, I'll just do this kind of as a bit of rough work over here. So we've got e to the x minus e to the minus x. So we're going to have e to the 2x, e to the x times e to the x, adding the x's together to give e to the 2x. Now this times this is negative 1, and this times this is also negative 1, so that will give us a minus 2. And then we'll have plus e to the minus 2x, again adding those powers, minus x and minus x, to get that power in that product. So we will have e to the 2x minus 2 plus e to the minus 2x. And so we can see from this that what we'll be left with is a half of e to the 2x and e to the minus 2x. And we can see that this is exactly the definition of cosh, but with the x replaced by 2x. So this is cosh of 2x. And just to point out what happened in the algebra here, we've got a 1 here, and we've got a half times minus 2 here, so that will be a negative 1. Those have cancelled in that line of algebra there. So that's the start of the question, and then moving into part B, we've got to solve an equation. So this involves cosh 2x, sin x, and 15. We now have a way of replacing cosh 2x with an expression involving sine x, and so we may as well do that because that will give us a quadratic in sine x. So let's just have a look at that. So I'm going to start with the equation that's been given to us, cosh of 2x minus 3 sine of x equals 15, and I'm going to replace cosh of 2x with 1 plus 2 sine squared x, and so we've still got minus 3 sine x equals 15, and I'm going to rearrange this to make it look like a quadratic. So I'll put the squared term first, 2 sine squared x, and then the sine term, and then we're going to have negative 14 here. And let's see whether this will factorise. So we'd need something like 2 sine x here in one of our brackets and sine x in our other bracket. Yeah, so if we take negative 7 here and plus 2 here, you can see that that will give us the correct factorisation. We'll get negative 14 minus 7 sine x plus 4 sine x, which will make that, and we get the right number of sine squared x. So there are two possibilities then. We've got sine x equals 7 over 2, or sine x equals minus 2. Now both of these are possible because sine x will take all real numbers, so you can have sine x is 7 over 2, and you can also have sine x equals minus 2. Now what we're going to need to use here is our log expression for inverse sine. So in the first case we have x is inverse sine of 7 over 2, and of course in the second case we have x is inverse sine of negative 2. Now I'll just put the expression up for inverse sine of a value. So let's express it in terms of u so as not to get confused there. So that will be log of u plus the square root of u squared plus 1. So let's have a look at how that works with our two values here. So we've got x equals log of 7 over 2, and then we've got square that, so that would be 49 over 4 plus 1. And in the second case we've got x equals log of negative 2 plus the square root of, well, 4 plus 1 this time. So this will give us two values then. We have x equals log of, well, so looking at this expression here, we've got 49 over 4 plus another 4 over 4, so that'll be 53 over 4, and so we'll get something like 7 plus square root 53 over 2 for the first value, and we can't really do anything with the other value to simplify it, so we'll just have to write that as minus 2 plus the square root of 5 there for our two values. So let's have a look at the mark scheme for this. So you can see, yeah, we're starting with the right hand side, a method mark for that. For the multiplication of this squaring of this bracket, another method mark there, and recognising that as cosh 2x to get 3 marks. Here we have the quadratic in sine and factorising it for 2 marks and getting solutions in for sine x for a mark, and then using the method of the inverse sine in terms of logs to get another 2 values here to pick up all 5 marks. Okay, let's have a look at the next question. So we've got a curve this time defined in terms of sine, and then a curve just defined in terms of the exponential function. It says sketch the graph on one set of axes given the equation of any asymptote and the coordinates of points where the curves cross the axes. Okay, so let's start with C1 first of all. So I'll draw, let's just think about how we might think about this. So a graph of sine will look like this. It goes off to infinity and minus infinity. As it passes through the origin there, it's got a gradient of 1, so this is y equals sine x. And we can think about C1 in terms of that, because the 2 is going to give us a kind of squashing towards the origin, and the 3 is going to give us a stretching away from the x-axis. So it will kind of look similar to that, but it will actually be a lot steeper at the origin than that. So it'll be something like this perhaps for C1. So this is y equals 3 sine of 2x. And then C2, if we look at that, Well, I guess it's useful to know what e to the x looks like for this. So e to the x is like this. So for big negative values we get very small numbers, and then it obviously it hits 1 when x equals 0, and then it goes on and increases. So for a big negative value, this term here will be very close to 0 but positive. So what we'll get there is values just a little bit less than 13. So if I mark on y equals 13, that will actually be our asymptote, and then you can see that when x is 0 we're going to get 10 for this, so we'll get 13 minus 3, and so the graph will be something along the lines of this, and it will go down from here, and we can work out where y equals 0. So if we take curve C2 and we set y equal to 0, we get 0 equals 13 minus 3 e to the 2x. So that means that e to the 2x is 13 divided by 3, and 2x is log of 13 over 3, and x is half of that. Okay, so that means we've got a point here where it cuts through the x-axis, and we've got that value there is log of, it's a half log of 13 over 3. And this value here is 10 on the y-axis, and this is the origin, of course. So we need to write down the coordinates of where everything happens here and the asymptote. So for C2 we've got horizontal asymptote y equals 13, we've got intercepts at 0, 10 and a half log 13 over 3, 0. And then for C1 we've got no asymptotes, but we've got it cutting the x and y axis at the origin. Okay, now we've got to now solve this equation. So we can see then that there's only one solution of this equation. So what we're actually effectively being asked to do here is work out what the x coordinate of that point there is, because that will correspond to the solution of the equation. Okay, let's have a look at how this will work. What we need to do here is work in terms of e to the x and get an expression in terms of e to the x. So I'll start with the equation as given. And we'll immediately switch that for e to the 2x minus e to the minus 2x over 2, replacing sign of 2x there, equals 13 minus 3 e to the 2x. And at this point I'll clear out all the fractions. So I'm going to multiply through by 2. So we have 3e to the 2x minus 3e to the minus 2x equals 26 minus 6e to the 2x. So now moving that across, 9e to the 2x minus 3e to the minus 2x minus 26 equals 0. And now what I want to do is just multiply that through by e to the 2x, so that we'll actually have a quadratic then in e to the 2x. So it'll be 9e to the 4x minus 26 e to the 2x minus 3 equals 0. Okay, so now I'm looking to see whether I can actually factorise this. So it would either be, I'll do this at the top, it will either be a factorisation like this with a 9 and a 1 in front of e to the 2x, or it could perhaps be like this, I guess, with 3e to the 2x and 3e to the 2x. Now I'm favouring this one because I can see that the 3 here, I can write that as 1 times 3 and I can get 27e to the 2x, which looks close to this. So I think I can see how this works. We're going to have 9e to the 2x, and we're going to have e to the 2x equals 0. So we have we'll have negative 3 here and plus 1 here, and now we can look to see how these solve. So continuing the work here, we've got e to the 2x is minus a ninth. And of course that won't work, so that's for the first bracket, so that's not possible, because e to the x is e to the anything is positive, so e to the 2x can never be minus a ninth, or we have e to the 2x equals 3. So this means that 2x is log of 3 and x is a half log 3. And that will be our solution in the form of half times log of an integer. Okay, let's have a look at the mark scheme for this then. So here are our graphs. We've got the asymptotes, we've got this value for the x-intercept and 10 on the y-axis, so we've got 4 marks for those features of the graph. Then we're going to use the definition of sine of 2x here, getting a quadratic in e to the 2x with solutions like this, and we're picking up quite a lot of marks for that method. And finally x is a half log 3, and so that's a nice question based on some standard techniques. Finally, we'll look at some differentiation here of inverse cosh. So what have we got? We've got y equals arc cosh of 3x squared, and the first thing we have to do is show that this differential equation is holding for this function. So it's a relationship between y and dy by dx and x. I think in order to do that, it's probably worth reminding ourselves of how arc cosh of x actually differentiates. So if we just differentiate that with respect to x, that will give us 1 over the square root of x squared minus 1. Okay, so what I'm going to do down here, where we have this function, is I'm not going to even do anything with this yet. I'm just going to work out what dy by dx is. So this is quite complicated because it will be the chain rule a couple of times actually. So by the chain rule, this 2 will need to come down. We'll also need to differentiate this bracket, which means we'll get another factor of 3 at the front. So we differentiate arc cosh, but then we're applying that with 3x, so it'll be 1 over, and rather than just x squared, it'll be 3x squared minus 1. And then of course we're going to have the original bracket there, but to the 1 less power, so that will just be arc cosh of 3x. So it looks like dy by dx is 6 over the square root of 9x squared minus 1 times arc cosh of 3x. Okay, so what I'm going to do next is I'm going to substitute that into the left hand side as dy by dx there. So substitution of that into left hand side in part A will give us, we've got 9x squared minus 1, and now we need to square this, so it'll be times 36, and we'll get a 9x squared minus 1 in the denominator, which should be helpful. Arc cosh of 3x and all squared. So we can cancel these bits, and we can actually see that what we've got there is 36 times the original function y, because y was arc cosh of 3x. And so that will conclude part A. Part B is potentially quite tricky. A difficult way to do this is to work out what the second derivative of y with respect to x is using this expression here, and it's a product of course, and it's got some quite complex differentiation within that product. There is a neater way to do this, which is to notice that if you go through and differentiate all of this with respect to x, so the left hand side and the right hand side, then because of the way that the product rule works, you get something very much like this. So what I'm going to do is I'm going to take the answer to part A, I'll just write that out again here, and I'm going to differentiate it with respect to x, so left hand side and right hand side. Now the left hand side I'm going to treat as being a product of this function and this function here, dy by dx squared. So let's have a look at that. So we're going to have 9x squared minus 1, and then we're going to need to differentiate dy by dx squared. So again, this is the chain rule. So the 2 comes down, we differentiate that bracket, which will give us the second derivative, and then we're going to have the bracket, but just the power of 1 this time. So then to conclude the product rule, we're going to have 18x, which is the different derivative of this bracket, times dy by dx all squared. That's the left hand side finally differentiated. The right hand side differentiated is just 36 times dy by dx. So you can see here everything is multiplied by dy by dx, and we can cancel that as a common factor. So we get 9x squared minus 1. I'll put that 2 in front of that. So this has gone, one of those has gone, and this has gone by division. So we get d squared y by dx squared plus 18x dy by dx equals 36, and then I think all I need to do now is divide everything through by 2. Everything is even here, so we get 9x squared minus 1 d squared y by dx squared plus 9x dy by dx equals 18. And so there's a nice way to work out the second part of this question, which is worth looking out for in questions similar to this, I guess. Can you just differentiate one of your answers again using implicit differentiation, product rule, chain rule, all those things? Will that be the way to do it? Is that actually easier than differentiating your direct expression for dy by dx? If we look at the mark scheme for this, you can see that there's this quite difficult differentiation here using the, well, it uses the chain rule twice and the derivative of arc cosh, so there's 3 marks for that, and then plugging it all in and showing that it all kind of settles down and you get the statement, another couple of marks there. And then finally here, yeah, here's the method which uses the product rule differentiation and then cancelling some of the terms, the dy by dx and the 2, to get that statement, and that's worth 4 marks. Okay, I hope you found that useful. There are another 3 recordings for Edexcel FP2, so hopefully you'll find those useful too. Thank you very much.